Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss centrifugal pump drivers, electric motors and steam turbines and their limits. There are three types of limits on centrifugal pumps. Impeller limit. This was the subject of our lecture on centrifugal pumps fundamentals. Sometimes this is called a pump limit. Driver limit. This means the electric motor is tripping off on high amperage or the turbine is running below its set speed. Suction pressure limit. Usually called lack of net positive suction head, NPSH, this is the subject of our lecture centrifugal pumps, suction pressure. Electric motors. Pumps are driven by either fixed speed or variable speed motors. Variable speed motors are becoming increasingly common. Flow can be controlled by varying the pump speed with the motor and thus eliminating parasitic energy losses across a flow control valve. However, because of the extra electronic components needed for a variable speed AC motor, 95% of the motors we work with are fixed speed alternating current motors. I will only discuss fixed speed, alternating current, AC, motors in this lecture. Direct current, DC, motors are sometimes used in process plants. It is easy to manipulate the speed of a DC motor. But direct current is almost never available on a process unit. Our motors at home are mainly alternating current motors operating at a fixed speed. A process motor in an American, Canadian, or Latin American plant is likely to run at either 1750 to 1800 RPM or 3500 to 3600 RPM. In other locations, a motor will likely run at 1500 or 3000 RPM. In the United States, they use alternating current at 60 Hz cycles per second. In Europe, they use alternating current at 50 Hz cycles per second. As the alternating current cycles 20% slower in Europe, the motor spins 20% slower. At home, our motors are single-phase. At the plant, the motors are usually three-phase. There is an important difference between a single and a three-phase motor. The three-phase motor can also be used as an electric power generator. The single-phase motor we use at home, without modification, cannot be used to generate electric power. The difference is important in that I once used this fact to avoid tripping off a critical process pump, as related in the following story. Helper turbine. Picture is a sketch of a centrifugal pump driven by a three-phase motor with a turbine helper. This particular pump was charging a light gas oil stream to a high-pressure hydrocracker. The pump was operating quite close to its design conditions of delta P equals 2000 psig. Flow equals 17,000 barrels per day. Specific gravity equals 0.80. Temperature equals 400 degrees Fahrenheit. Speed equals 3,600 RPM. The operators were not operating the turbine. The turbine was spinning, because it was coupled to the pump, but there was no motive steam to the turbine. The operators reported that the turbine was not needed, as the motor was pulling only 90% of its maximum amperage load. The question is, dear gentlemen, whether the pump will run faster if the motive steam flow is open to the turbine. And the answer is no. While the turbine will produce shaft work, and will help the motor spin the pump speed will remain unchanged. The extra shaft work from the turbine will just reduce the shaft work required from the motor shown in picture. The amperage load on the motor will just be reduced. But suppose the amp load on the motor drops to zero, by gradually increasing the steam to the turbine. Then let's suppose we increase the motive steam to the turbine by another notch. Will the pump, the motor, and the turbine, which are all coupled together and, hence, must run at the same speed, now run faster? The answer is no. But what will happen to the increment of shaft work generated by the turbine? This extra shaft work will be converted to electrical power. That is, the three-phase motor will turn into an electrical power generator. it will begin to export electricity into the grid. A single-phase motor does not have this sort of capability. Another way of expressing this idea is that the three-phase motor acts as a brake on the turbine. The motor can run at only 3,600 RPM as long as it is connected to the electrical grid. The only way we can get more flow from this pump without reducing the pump's delta P is to raise the specific gravity of the liquid being pumped. If the liquid is cooled from 400 to 200 degrees Fahrenheit, its specific gravity will increase by about 10%. This will allow us to get the same delta P with about 10% less feet of head. This will allow the pump to run further out on its performance curve. The pump will now pump more liquid, and the flow of light gas oil to the hydrocracker could be, and was, increased from 17,000 to 23,000 barrels per day. Question: how does this affect the amp load on the motor driver? Well, the feet of head has gone down by about 10%, and the specific gravity has gone up by about 10%. Therefore, the horsepower or work per barrel of liquid pumped remains constant. But the number of barrels has increased by 600 barrels per day, or 35%. Then the amp load on the motor driver would also increase by 35%. If I had not remembered this prior to cooling the hydrocracker feed, the motor would have tripped off. As it was, I had the steam to the turbine increased so as to decrease the motor amps to 60% of maximum before cooling the gas oil. Omission of this detail would have had embarrassing and possibly negative contractual consequences. Selecting motor size. We noted in Centrifugal Pumps Fundamentals lecture that increasing the impeller diameter might require a larger motor for an existing pump. Suppose, then, when a new pump is purchased, we install a 100 horsepower motor sized for the maximum 10-inch impeller, which the pump could accommodate. Actually, only an 8.5-inch impeller would be used in the pump initially. This 8.5-inch impeller requires only a 60 horsepower motor. If we install a 100 horsepower motor, what percent of the electrical power of the oversized motor is wasted? Essentially, none. The amp load on the motor driver is determined by the work done by the pump, not by the size of the motor. The amp load required by the motor is proportional to pump head times specific gravity times liquid flow divided by motor efficiency. There will be a small loss of 3% in motor efficiency by using an oversized motor. As process operators and engineers, we can ignore this effect. It is good engineering practice to purchase new motors for the maximum size impeller that can be installed in a pump. Motor trip. Point factors that increase the amp load on a pump's motor driver are: increasing the flow, provided the pump is running on the flat portion of its curve; increasing the specific gravity of the liquid pumped; increasing the impeller size. A 10% increase in impeller size may increase the motor amp load by 33%. Motor winding deterioration, which happens as the motor ages, depending on how hot the motor runs. Dirt buildup on the motor's cooling air fan guard screen. Most operators forget to clean this screen. The dirty screen then restricts airflow to the motor, which then runs hotter. A hotter motor will pull more amps. I recently reduced the amp load on a motor by 3% by cleaning a badly fouled screen. The amp meter on the motor breaker indicates the amps being pulled by the motor. Next to this meter should be a tag or a penciled number indicating the full limit amp, FLA, point for the motor. Above the FLA point, the motor should trip off. Operating the motor substantially above its FLA point will burn up the motor's windings. This is not quite true. Whenever we start a pump, the starting torque required to get the pump spinning requires a surge of motor amps. To avoid tripping off the motor on high amps, there is a time delay built into the trip mechanism. This delay permits the amperage load to greatly exceed the FLA point for up to 15 to 30 seconds. This is too brief a period in which to overheat the motor. If we cannot open the discharge control valve of a centrifugal pump 100% before the FLA point is reached, then we say that the pump is driver limited. This is a frustrating problem for plant operators, and clearly reflects poor design practice in undersizing the motor driver horsepower. Thermal protection. I have made the statement earlier in this lecture that alternating current motors operate at a constant speed. I said this because I've read it in a book. Yet, I know from personal experience that this is wrong. I know that my wood turning lathe will slow down if I press too hard on the spinning wood with my cutting chisel. The lathe is run by a 1750 RPM, 60 Hz, 120 V, 3x4 horsepower AC motor. But I also know that if I run the motor at a slower speed for a minute or two, the motor will get hot and trip off on its internal thermal trip switch. I will then have to wait 10 minutes for the motor to cool off before I hear the click of the trip resetting. The motor has gotten hot because an alternating current motor efficiency goes down a lot when it runs below its rated speed. That is, running an alternating current motor slow increases the motor amperage requirement. The extra amperage goes to heat and not to increased motor work output. At the plant, our motors are protected differently than at home. At home, our motors share a circuit with other power consumers. A circuit breaker may be rated for 20 amps, but a single motor on that circuit may be rated for 5 amps. The circuit breaker setting of 20 amps is too large to protect the motor from overheating. At the plant, each motor has its own dedicated circuit breaker, set individually to protect a particular motor from overheating, that is, the full limit amperage point. If the load on the motor increases too much because the specific gravity of the fluid pump has increased, the motor may indeed momentarily slow down. But due to the lower efficiency at the slower speed, the amperage load will increase rapidly as the alternating current motor slows. The FLA point on the circuit breaker in the breaker or switchgear house for that motor will be exceeded and the motor will trip off. To summarize, at home, motors can run slower for a minute or two before they trip off on high winding temperature. At work, motors trip off at the breaker after a few seconds of running slow due to the high amperage load exceeding the breaker full limit amperage setting of the breaker. Motor bearings. If you think a motor is running rough because of bad bearings, have it uncoupled from the pump. Run the motor alone and see if the vibrations persist. Motor bearings commonly fail because of a lack of lubrication. Most motors are lubricated with a heavy grease injected through a grease fitting delivered via a grease gun. Over-greasing can burn up the motor bearings. You need to follow the manufacturer's recommendations. A typical, but not general, program for motor bearing lubrication is 3 or 4 squirts from a grease gun every 6 months. There is a device now available on the market called a bearing buddy, which delivers a consistent grease supply pressure over an extended period of time. Motor bearing failures on one process facility disappeared when these bearing buddies were installed. Turbine drives. A turbine-driven pump is said to be driver-limited when the governor speed control valve is wide open. This speed control valve is usually called the Woodward governor. It is not that easy to see if the governor is really wide open. A few simple methods to make this determination are: increase the pump's flow. If the turbine slows, the governor is wide open. Increase the set point speed. If the turbine speed fails to come up, the governor was already wide open. Throttle on the steam supply to the governor. If the governor is already wide open, the turbine will slow down. Even if the governor steam inlet control valve is 100% open, it may still be possible to increase the supply of motive steam into the turbine. The position of the governor when it is wide open can often be reset to admit more steam flow. I once increased the flow through a crude tower bottom pump by pushing hard against the base of the governor and forced it to actually open to its maximum position. The pump speed came up 300 RPM, and the flow increased by about 15%. Another possibility is to open the speed or hand valves, as described in lecture on steam turbines. This will introduce more steam into the turbine case and slightly lower the pressure in the steam chest. Even though the governor steam speed control valve is wide open, the reduction in downstream pressure in the steam chest will increase the steam flow into the turbine. Of course, increasing the motive steam pressure will greatly increase the horsepower available to the turbine. First, more work can be extracted from each pound of the motive steam, and second, increasing the steam pressure will increase the pounds of steam flowing through the governor. Reducing the turbine exhaust pressure will not significantly increase the steam flow to the turbine. However, reducing the turbine exhaust steam pressure will increase the amount of work that may be extracted from each pound of steam. For example, 150 psig, 400 degrees Fahrenheit steam is being used to drive a turbine. The exhaust steam is flowing into a 15 psig steam header. By venting the steam to the atmosphere, the amount of work that can be extracted from each pound of steam will increase by roughly 30%. Check the Mollier diagram. Increasing the size of steam nozzles. Many steam turbines do not have full-ported steam nozzles. The existing steam nozzles may then be exchanged for larger nozzles. An increase of nozzle diameter of 10% would increase the turbine horsepower by 20%. Finally, the steam turbine's buckets can foul with hardness deposits from the steam. This reduces the turbine efficiency and may prevent a pump from running at its rated speed. Injecting steam condensate into the steam supply can remove such deposits. It is quite important not to operate a turbine-driven pump by manually throttling the steam flow to the turbine. Let's assume that the operators have set the turbine speed at 3,500 RPM by adjusting the steam inlet gate valve upstream of a malfunctioning governor. Suddenly, the discharge flow control valve cuts back, and the pump's flow decreases from 2,000 to 1,200 GPM. The pump speed will then increase, because fewer pounds of liquid are being pumped and less horsepower is required to spin the pump. The pump speed rises to 3,800 RPM. The trip speed has been set at 3,750 RPM. The turbine's overspeed trip is unlatched, and the machine shuts down. The operator relatches the trip, but every time the flow is throttled back, the turbine overspeeds and trips off. Finally, the operator, in frustration, decides to wire up the trip so that it cannot unlatch. As an operator in Refinery stated, when the governor won't work on a turbine, it is necessary to wire up the trip. I thought he was joking, but he could not have been more serious. Well, the operator did have a pump with an inoperable governor speed control valve. He did wire the trip open. A few days later, the pump briefly lost suction, due to a slightly low level in the flash drum feeding the pump. The pump cavitated, and the flow was reduced. Reducing the flow to or from a centrifugal pump reduces the horsepower load on the driver. As the steam flow to the turbine driver was fixed, the turbine started to overspeed. The excessive speed damaged the pump's bearing. The resulting vibration fractured the seal flush oil line to the pump. The flush oil ignited on the 700 degrees Fahrenheit pump case. A nearby worker was sprayed with the burning oil and killed. This is a true story. Gears. On occasion, pumps are not directly connected to either a motor or a turbine. There is an intervening gear, which can increase the pump speed by multiplying the driver's speed. The gear is another source of possible misalignment and vibration. I have always considered such reduction or speed increaser gears to represent poor design practice, and an unnecessary complication as they often require their own lubrication system. Most often the lube oil pump is driven indirectly by the main pump. Especially for a turbine-driven pump, this is a recipe for disaster. It's true that the primary lube oil pump is typically backed up by a separate, spare lube oil pump driven by an external power source. However, only too often that backup pump, which is rarely used, fails to start up automatically due to lack of routine testing, and the gears are destroyed. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.